Good morning to everybody. We will start the session of this morning with Alfredo Guevara that will be talking about decoding celestial holography. Please go ahead.
All right. Can you all hear me? Great. Okay, great. So that delay actually was intended because this talk is really short. So I was actually trying to extend the delay as much as I could. But yeah, so I'm a bit jet lagged and I have some cold, so it's a bit. We're gonna try to do our best. So by the end of this talk, maybe you won't fully believe that we do live in some error correcting code, but at least I hope I can convince you that this is one of the important questions that maybe should be higher up there in the priority lists. And I'll be happy to discuss also the aspects and limitations of this work. So this is mostly based on some paper that just appeared in JHEP with Yang Re, who is the BIMSA in Beijing right now. And I should also encourage you to read this new paper we have coming, hopefully this weekend, with Noah Miller and Mina Hinwich, where we elaborate on certain aspects of gravitational amplitudes from the perspective of CFTs, kind of analog or parallel to what Walker was telling us yesterday in a large N limit. But this won't be this talk, and this talk is called Decoding Celestial Holography. So let me just introduce 3 questions that should get us going. The first one is sort of a basic question, which is whether celestial CFT is an IR fixed point or some discrete system that we can build in a lab. If that was the case, then the first order question would be, what would that lattice mean, or where would that lattice exist, and in what sense is related to a celestial sphere? So we know that CFTs lie at fixed points or certain condensed matter systems, and we have technology to take continuum limits of these systems. So we want to understand whether a celestial picture can emerge in such a way. So this is a kind of a first order curiosity. And of course, a subleading order curiosity is whether we can understand the vast landscape of IR phenomena that we all know and love by now, especially patterns of symmetry breaking, including what identities coming from subtheorems and all of that. How can they arise in the continuum from a discrete Hamiltonian? So as a motivation to just convince you that this is not such a nonsense question, let me just briefly mention that there are models of ferromagnetism in which we have very well understood, or condensed matter people in particular have understood symmetry breaking patterns. These are not precisely spontaneous symmetry breakings because we are talking about discrete symmetries now. But nevertheless, they exhibit certain sort of extended notion of symmetry. So one of these examples is a magnetic field operating as a background field in a spin system, or in a lattice, or in a glass system, if you want. And there is an extended symmetry operating in such a case that people sometimes call Landau levels, or there are many different names of this, but it stems from this sort of algebra. This is a particular algebra for the XY system, it's a spin chain. And a continuum limit of this condensed matter system leads you to a 2D NLSM, which has an anomaly, as explained in this nice work by Nati Sadler. So this slide, well, if it had a smell, it smells like 2 things. Landau levels smell a little bit like protection of some particular observable. In particular, thanks to Kitaev, we know that Landau levels can be used to protect quantum information in the toric code. So it has some notion of that. But there is also this 2D NLSM, which smells a bit not like the space-time. So we are here talking about a condensed matter system. So there is no space-time, there's no celestial sphere. So when I talk about the continuum limit, this 2D is not the 2 dimensions of the celestial sphere specifically, but perhaps something else. And I'm sure some people here have some notion of what that else could be. So it's a 2D CFT somewhere else. Okay, so there's a second order question, which I won't derail into for this talk. But it's the fact that error correction has taught us about how to do holography in condensed matter systems. So even those SYK developments from the recent years kind of stem from the idea of thinking of a tensor network picture that tiles, if you want, the hyperbolic geometries. So those are examples that are kind of toy model because we don't really live in such a geometry, but so far they have taught us how to do condensed matter from this perspective. But if you're not interested in that, the sort of bottom line of these ideas is that, well, actually, when we have a condensed matter Hamiltonian, we have a discrete finite system we can put in a box, and in this box we can sample. And the technology of Monte Carlo sampling is actually very well developed right now. So all of these condensed matter systems are very suitable for Monte Carlo. And that's exactly what people do to test ideas regarding gravity nowadays, but also regarding all kinds of systems. So I just want to invite you to think about how to really realize such systems in such a setup. Okay. So with that said, let me just jump into the overview. Roughly speaking, what we're going to try to do is build something like a quantum error correcting framework that's ad hoc to celestial holography. And the sort of the slogan here is going to be embedding an encoded system into claim space. So the first question that pops up, why do we need claim space? Well, claim space is defined by some reality condition. In a quantum system, that reality condition, so you take a real slice of your complexified Minkowski, that reality condition translates to hermiticity of certain operators that we need to define the spectrum of this error correcting codes. So that's why we're working in claim space. I'm not claiming that's the right option, although I'm sort of tempted to think that way, but it's certainly one way in which we can move forward. Okay, so the output of pushing that direction is summarized in this table. So it's this kind of an executive summary of the whole results. So it's an equivalence between different aspects of the error correcting construction. So in particular, we have logical states. Those will be mapped to hard graviton states, which are the ones that carry information about the S matrix, the finite part of the S matrix. There will be some notion of how to quantify quantum information that has certain implications in terms of what we understand usually as super translation charges. So all the infinite modes of the super translation curve will be sort of quantifying this quantum information. There will be a discrete analog of what we call W1 plus infinity, which is not Wn, but it's a cousin of Wn, so classical cousin. But the keyword here is discrete. That will map to, in a large n limit, will map to W1 plus infinities of current. And so all of these three aspects, I would say, they are more or less well understood. But there is a fourth aspect, which is a sort of work in progress that is actually very challenging, which is to actually implement logical operations. I should say that this discrete symmetry is actually an error in this framework. It's a very soft sort of operation that doesn't alter the quantum information. But these logical operations are sort of hard unitary gates that interact with our observables and so on. And this is kind of the challenging aspect of this program. But again, there's still a lot to discuss. Okay, so that's the outline. So let me just give a bird's eye view of what the error correcting code usually means. This is going to be a sort of notation setting slide. So what is a stabilizer? Okay, so that's just a way of calling an error correcting code. An stabilizer code is defined by an abelian subgroup of Pauli group. So we should think of Pauli group as all of the logical operations we can do on certain number of qubits or qubits. I will define those. So these logical operations have a special subgroup that is abelian. Okay. So what this means is that, well, essentially each of these generators is a label. So in the same way that I define charges by labels, these stabilizers are just labels of my states. The cost of space is the one that's labeled by 1. So if all the stabilizers have 1 eigenvalue, then I find I am in the code. So logical operators commute with S. That means they don't change these labels, and they keep me in the code. But obviously are not trivial, so that's why they cannot be in the stabilizer. Okay. Errors that anti-commute with some S will shift. Operations that anti-commute with S will shift the error syndrome and can be diagnosed. So the grammar didn't help me there, but essentially what I'm saying is that if the eigenvalue is not 1, so I assume it's going to be a small fluctuation of the eigenvalue, then for small enough eigenvalues, I can diagnose that and I can correct it using some of the algorithms. Any questions about this? This like sort of the setup for the program? Okay. Okay, then we can get into a particular version of the stabilizer code called Gottesman-Kidar-Presque. So the idea of these GKP codes is that sometimes we can have access to certain continuum system. One example of this is an oscillator. So I think of the coherent states in the oscillator as labeled by a parameter alpha. And that alpha is, just a continuous variable that I can sort of measure if I have a laser or something. So sometimes I can imagine my wave function. Sometimes in this wave function, there will be errors. And these errors can either shift the amplitude or the phase of the wave function. So we can say that, there will be some dephasing of the wave function that's really small, or maybe sometimes there will be some amplitude error. Okay, but this happens in signal processing. It's some classical effect. You can think of this as being some kind of gravitational wave in a way, but there is a particular way of protecting against both of these phase and amplitude fluctuations, and that's what Gottesman, Kitaev, and Presque designed. So instead of thinking of the wave function, they propose to think of the Wigner function. So the Wigner function is labeled by x and p, position and momenta. Here, let me just call them suggestively lambda as some kind of momenta. So lambda has a conjugate. So essentially, lambda is a classical version of mu. And mu here is essentially x and p. I'm going to write it in just to make everything clear. There's an I here. There will be some h bar that I'm going to call tau just for convenience. And so in this setup, I can define stabilizers that are given by these operators, where n is just some integral. Okay, so why are these important? Well, obviously, this system has a symplectic symmetry, so I can rotate this mu plus into mu minus. And if I want to find some state that diagonalizes or sort of is invariant under this symmetry, what I need to do is I need to construct an abelian group, which gives me some abelian representation of this symmetry. So you can see that these generators actually become abelian when tau or when n is an integer. Okay, and so then the code just is standard. the code states are defined by this condition. The logical operators are defined by this condition when lambda is an integer, and you can see that that's going to shift the eigenvalue of S. Okay, so we know from GKP that this sort of construction protects against small shifts. It's a little bit of algebra to show how to correct these shifts, but you can sort of measure the shift just from the stabilizer. So that's sort of the setup. So you can think of the phase space now as being discretized. Essentially, this is a point in phase space I label by lambda plus and lambda minus. It's like my Wigner function lives here. Then there is some shift in my Wigner function that either shifts x or p. And if that shift is small enough in the units of the lattice, then that can be corrected. Okay, but now the question is, what is this lattice and how do we actually realize it in physics? So I claim that this lattice is related to the celestial torus. So to see that, let me just give an overview of the celestial torus. I'm going to focus on these two cycles of Klein space, which we have seen many times, I believe, in this conference. So I'm going to fix my R1 and R2 as some particular radding. And I'm going to look at the celestial torus at sort of a finite location in the ball. Okay, and it's going to be important to work with null coordinates, just because this define kind of left and right movers in this torus. Okay, so let me just give you sort of a cartoon-ish picture of what's going to happen. So I'm going to go to certain particular location in this ball, and I'm going to blow up the celestial torus. And I'm going to insert a particular chain along one of the cycles of this torus. It's going to be a null cycle. And in this chain, there will be some sort of code that is, each mode of this code is related to one copy of the GKP space. Okay, so let's see how that works. Well, imagine you have a field. I call it twistor field, but that's it's just a field in a sense. It's just a name that lives in this circle, one of the cycles of the torus, and has a particular mode expansion. These modes, if I quantize this field, I'm going to quantize it in this way, just standard canonical quantization. Then that is exactly what leads me to this algebra. I'm going to give you the physical system in a second, but just assuming that I have this field, it's a spin 1/2 field. I can quantize the modes as follows. But this is an infinite system, right? It has all the Virasoro redundancies. So I'm just going to truncate it, okay? Because I'm after a condensed matter system. So we can truncate it in a symmetric way that's consistent with a subgroup of Virasoro, and we keep certain modes up to n. So that essentially gives us n copies of this algebra, which has a symplectic certain SPN symmetry. Now, let me say that there's a particularly nice truncation when n is 2, in which you have only, say, the global modes here. So if n is 2, I only have a mu plus and a mu minus. And if I think of this essentially as a twistor, now is when the twistor word enters, then this mu is related to the space-time by something called the incidence relation, where lambda here is some coordinate that I can set in the torus as being an angle. So lambda is essentially a direction on the celestial torus, and through the incidence relation, this gives me modes of mu that are plus or minus in x plus. And so essentially what these modes here are is components of my x in the space-time. Sorry, I hope everyone can see. And when these modes of x are plugging into this relation, then what you find is a non-commutative version Klein space. So that's kind of the simplest case in which quantizing this field actually leads to some interesting geometry. But you can consider all the modes, not just the global part, and then it actually becomes much, much richer. I'm gonna sort of skip through the GKP construction because I know like this is not a quantum information audience, so I actually myself I'm definitely not an expert, but I will outline the key steps that one needs to take to actually derive the code from this algebra. And the first step that GKP tells us is that, well, we essentially need to renormalize this tau. If it's not a discrete parameter, we need to make it discrete. And we make it discrete by normalizing these operators in a particular fashion that depends on a particular integer n. So if this was an h bar, it would be just completely continuum. But that's what we need to do to generate a discrete system, in particular to generate the code. When you have this, then each of these pairs gives a copy of the code.
Excuse me.
Yes.
This Klein, it is with signature -2.
Yeah.
How can we see from here?
That follows from the fact that these mu's are Hermitian. So that's what I mentioned in the beginning. So in the Klein space, mu's is a real variable, and essentially is conjugate to a component of the momenta, which is a lambda tilde, so it's real. And so the fact that these mu's are Hermitian actually goes back to Klein space. That's it. Okay. Wait. Sorry. I don't want you to look into this slide any further, so that's what I'm trying to do. Is there I think maybe the, okay. Okay, it doesn't work like this. Okay, so let me go back to the mode cutoff. I told you that we can get a copy of this of the GKP codes if we truncate these modes to be a discrete system. But to make it into a lattice, actually, we place this. It's not necessary to have a continuum field along the circle. It's just it's just necessary to sample it at endpoints, because those endpoints already have, in terms of signal processing, these endpoints already have all the information of the field mu(x). So I'm just going to label these fields by mu(j) when I evaluate them at the position xj, which is a particular position in the cycle. And then, well, these mu(i's) also satisfy isomorphic algebra, just because it's essentially a discrete Fourier transform from the modes. And again, in each of these sites, there will be a copy of the code. So I have my stabilizer in each of the sites. And essentially what I have constructed in phase space is a 2n dimensional lattice. For each of these copies, I have a 2-dimensional lattice. And in this setup, these mu's are discrete, and everything is discrete. So then we go back to this original picture I showed you, which is fluctuations in phase and amplitude that are bounded like this, according to GKP, can be corrected in this Hilbert space. Okay. So that's like the first step to make a connection to this finite system. We first define the finite system. Before even giving you what a Hamiltonian looks like, I can already write down the symmetries of that system, just because I have the states, and the states are given by GKP. So I'll give a Hamiltonian at some point. But we just analyze at first what are the symmetries. So obviously we don't have the full Virasoro because we have discretized it. But we do have a sort of discrete holomorphic. Well, we have many things. We have a full symplectic group. That's the starting point. It depends on the number of qubits I insert. But we also have sort of holomorphic transformation. So this holomorphic is in quotes because it's actually mimicking what the holomorphicity in twistor space is. essentially it's not going to mix up mu's of different chirality. So it will sort of rotate them internally. I believe there's a type here. There's an anti-holomorphic one, which actually rotates the index k, so it rotates the modes. And more importantly, there is a truncated version of Virasoro, which is essentially the truncation of my Virasoro generators that goes up to the mode n-1/2. So you can check that this little Virasoro is actually embedded, it's actually a subalgebra of the big symplectic symmetry. But the big symplectic symmetry has all kinds of interesting transformations. So it has a baby version of the Kähler sector that I think I forgot to write down. But it has all of the sort of symmetries that in the continuum will become the symmetries of a twistor space.
Is it just rotate from the algorithm?
Yeah.
So the one of us is
this one is mixing the K and Ls, so it's like a Virasoro transformation. This one is rotating. Yeah, it's rotating the. It does a rotation for each alpha. Yeah.
So
R depends on alpha. Each alpha has a different rotation. So it's not exactly a Virasoro de continuum. So you can compute the algebra. You don't need to take any continuum limit so far. You just need to truncate it carefully because there is an induced truncation in the generators. And you find that the central charge of this algebra happens to be -2. And because these generators are real, because we are in Klein space, we say that this is a free symplectic boson in the CFT side. You can also construct generators that look more like what will become W algebras. And for that, you just need to take, again, certain truncation. So I truncate my modes to add up to M. So if I had, say, M equals 2, then this would look like mu squared, which is essentially a L2 at a Virasoro. Yes.
So it's you restrict them and then it's smaller than the right, so you get bigger.
Oh, the ones that you set to 0. Yeah, the ones that escape, you set to 0. It's a consistent truncation. Okay. So that said, there is a discrete version of those things. Let me just mention that.
Sorry, could you go a moment back?
Yeah.
To see generators of W. If I am not mistaken, one has mu plus and mu minus, or another thing, Q and P, to certain power.
Yes.
And here, how I see that?
Well, I believe there is a small typo here. Sorry. You have to take the modes, including plus and minus, obviously. Yeah. So actually, this is just the top. This is just the top component. So yeah.
Okay.
Yeah. It has 2 n components at certain levels. So yeah, this actually is a type.
Is this pretty big W possibility?
No, it's not. Right now, I call it W, but it's truncated.
But is it truncated in relation to BP W?
Oh, okay. You're saying if I I get your question. So you're saying if I actually truncate, I believe it does. I believe it does. I don't remember at this moment, but I believe it does. we are taking essentially a classical limit where we take tau to be very small, and in that case, essentially the W algebra is kind of unique because it's the classical, it's the Poisson. Yeah. Yeah, but actually, it's an interesting question. What is the algebra at finite tau of these objects? Okay. These are interesting symmetries, but there's one particular subgroup of the symplectic group, which is not it's not either of those. It's not the holomorphic ones or those Virasoro or the W ones, but it's sort of instructed to us from GKP, and it's given essentially by this operation acting by conjugation, or if you want, acting on a state. So in this case, I take a particular unitary transformation. So if you remember that mu's are Hermitian and lambdas are real, this transformation is always unitary, but I constrain these lambdas to be integers. And in such a case, these act on the they commute with the stabilizers, essentially. So I remind you that operations that commute with the stabilizer are logical operations. And the group generated by this transformation is called the Clifford group. It's a very relevant in quantum information because these are essentially the gates that we can construct to manipulate the protected states. Okay, so let me take the large n limit. I will take the large n limit in two ways. So first, that will release this truncation. So it will release the modes to range from minus infinity to infinity. And it will affect also the tau parameter. And in doing so, you can check that all the copies of this symplectic algebra essentially just go back to the CFT, the OPE of a free boson, sorry, a symplectic boson. And I already showed you the central charge. We can match the central charge. It's a very simple, straightforward exercise. And obviously, we can parameterize it now in the null cycle of a celestial diamond, but we can also write it in these holomorphic coordinates. So obviously, the W generators just now become these normal order products of operators, which are spin 1/2, and sort of everything else just follows. But the sort of bottom line, I believe, of this construction is that you can sort of check many claims of correlation functions starting from the discrete analog. So if we go back to celestial holography, we expect correlation functions of any kind of operator with a bulk dual to have certain word identities. And if I associate these logical states with these positive helicity gravitons in the celestial picture, then I can check such word identities, even in the discrete case. Here, I'm just showing the continuum so that the notation looks more familiar. But nothing of this requires to take any large n limit or such. It's just a way to write it. So when I write this operator as essentially a coherent state made out of mu plus and mu minus, so mu plus and mu minus, you can think of them as some components of a plus graviton, if you want, but I'm not going to tell you what the exact definition is, just the algebra. If I write this state, then I can define such a correlation function just by doing OPEs between different mu's. And then I can check that this correlation function happens to have conservation of all these supertranslation charges, right? So the hard states are therefore eigenstates of all these supertranslation charges that are defined this way out of modes of my twistor field. And in the discrete limit, sorry, in the discrete case, they are quantized charges. So that means we have some notion of protection of the quantum information, but as soon as we take the large n limit, we are back in the sort of non-protected phase.
Sorry, in this discrete interpretation or the continuous discrete interpretation, are you recovering a sort of super rotations?
Good. So super rotation, yeah, this is a bit of a tricky question, but it's usually said to be embedded in W2. So actually, because of so there is chiral version of the super rotation that's just coming from the stress energy tensor of the symplectic boson. So you can check. Sorry, I didn't. Maybe I didn't write it here. But, yeah, you can compute things like this with the stress energy tensor of the symplectic boson, and you will find that you will find essentially the super rotations. But there is also a piece that comes from W2. If you consider just 2 copies of mu here, this will generate the loop algebra of an SL2R bar, which is okay. So I was here. I think okay. Let me just skip this slide. I think you can just take the discrete version and make it continue. If you write it in the sort of field variables rather than the modes. So here I write it in terms of the modes. In terms of the field variables, it looks like this, and then you can do OPEs with it. So that's sort of convenient for certain cases. But going back to the super translation charge, remember the super translation charge is a particular mode of this twistor field. So it's more convenient, perhaps, to write it in terms of modes. And remember that for each of the modes, I have a stabilizer, and I don't need to take such a continuum limit, a discrete or continuum limit to have a stabilizer, because I always have these modes that are discrete. So for each mode, I have a stabilizer, and my code is given by the eigenstate of the stabilizer. To have the code being eigenstates of the stabilizer with eigenvalue 1 essentially means that these operators here are discrete. This super translation here now becomes discrete. Okay, and if it is discrete, then that allows me to act with certain operators that are not discrete, are continuum, but are bounded in the sense that they look just like these coherent states of gravitons, but in the coefficients that you would have set to amplitude and phase, there is a particular bound, and this bound is related to how large n can be. Now, what happens is that if you take any single mode and act with such a state, you can essentially correct this action just by looking at the nearest integer of my eigenvalues. So, for instance, I think I have a picture here. If I act with a state that has bounded phase and amplitude, there will be a nearest integer in this case because it's a 2-dimensional lattice. It will be a particular point in this lattice that is associated to a logical state. So I think of the logical states as being in maybe 1-to-1 correspondence to this lattice. And the things that I can correct are actually soft in that sense. This is a particular mode M. It's a phase space slice, but obviously there are infinite copies of such a phase space diagram. Sorry, such a phase space. So here I'm just saying this, and essentially these are correctable again as long as the mode does not cross the integral boundary. Okay. So that's what happens in phase space. So let me try to zoom out a little bit and try to make back the connection to the space-time. So I haven't really told you what the space corresponding to the phase space of such a system is. But if you think about twistor space, you can have an idea that these are sort of the Fourier transform of the lambda tildes. And so lambda tilde is essentially a measure of momentum. So we should think of this as essentially the momentum space or the phase space associated to the space-time. So in this sort of momentum space, there is a particular window in my momentum sort of variables, say lambda and lambda tilde, where I can apply the error correcting procedures. Okay. So the operators I can write down happen to have a particular OPE. And using that OPE, I can actually compute a correlation function. And I guess at this point, you can imagine that this OPE is a particular extension of W. Let me just skip that slide. So the hard states here have quantized supertranslation charge. As I mentioned, this supertranslation charge is essentially lambda tilde. But for particular case, sorry, let me just say, this supertranslation charge is infinite, but as soon as lambda tilde is two parameter variable, then this will be just a momentum. Okay, so soft gravitons create small displacements in this charge. We can measure them and correct them. I haven't told you how to correct them. The algorithm is sort of convoluted, but the intuition I just gave you is that you can essentially always adjust to the nearest integral. And in doing so, we say that we apply a correction operator to these states. So if we think of these errors as being essentially soft, they are soft because the variables here, epsilons, are bounded. So that means that the energy is actually bounded by the energy here is bounded. So lambda tilde, imagine, is proportional to the energy. If lambda tilde is something like omega 1 z bar, and then the bound on the error is proportional, is of the order of 1 over n. So that means that for each energy and for each angle that satisfies this bound, I have an error that I can correct. And that's exactly the ones that correspond to IRFS. So all of these sort of fluctuations are infrared.
So that's the fluctuation bound. That's the error in the one.
Correct. So this is now an operation. So the operation, sorry, let me just write the truth. Yeah. So this operation you can think of as an operator acting on a particular correlation function, but it's also a state, right? And so this state is exponential of mu, which can be associated to a positive helicity graviton. So the operation is sort of a finite operation, which exponentiates the soft graviton creation operators.
So I wanted to understand if this is physically corresponding to a summing cloud of soft photons, or it's just one soft photon, and then you have to do the summation, and you always do the infrared problems. The problem is infinity times zero, infinite number of soft photons.
Yeah. So there are sort of two answers to that. I guess the first answer is, in this theory, which I haven't really specified, but it's a nonlinear sigma model for mu plus and mu minus. I can compute correlation functions. In this theory, this is a coherent state made of such a operator. But ultimately, we actually want to relate this theory to a gravitational theory with infrared effects. And for that, we actually do need to identify certain parameters of this theory, in particular, this tau, with some kind of infrared cutoff, right? So this theory will have a particular IR cutoff if it matches a gravitational observable. So at the end, we will propose that this tau is proportional to IR cutoff. I keep forgetting that I kind of. But yeah, so that is a very good question. Okay. So by construction, this will be IR finite because again, I'm just computing OPEs with a finite state. And this should come as a surprise because after all, we don't have infrared divergences popping up in twistor theories because they are protected by many symmetries. So we would say that we have recovered part of the twistor story from a discrete system, but we haven't really matched this infrared divergence because we need some sort of sensitivity to the infrared effects to match that. But if we were to write down a particular model that can match the correlation functions, it would be this action that's essentially a symplectic boson. It can be obviously, it's suggestively written like this so that it can be translated into what many people here have worked on related to the nonlinear graviton. But as it is, it's just a symplectic boson plus a source. Particular choices of this source are, of course, of physical meaning. In particular, because they can encode certain self-dual backgrounds. And Klein space is just the simplest instance of such. So actually, it would be interesting to include such a term in the discrete system as a Hamiltonian interaction, and actually understand the implications of that for the algebra and the symmetries. If such a term is going to preserve the symmetries, then it would have some nice continuum limit, and therefore it could match one of the symmetries of self-dual gravity. Okay, let me just skip some of these remarks because I already mentioned them. So I'll just jump to the outlook. Obviously, we have made a theory essentially of positive helicity gravitons. So part of the ingredients are still missing. Obviously, part of the story with the nonlinear graviton is always to include the negative helicity sector in a smart way that doesn't violently destroy the symmetries that we have. There's a particular connection between this and color kinematics duality that I sort of outlined in one of my old papers, but essentially stems from the relation again to W symmetry realized in the lattice. We can ask about the bulk interpretation of this. Can this code be seen as a many-body chain in the Klein space? So that's kind of what I was hinted to when I was showing a picture of a Klein space with a particular vibration given by this torus. So you may ask, what is this discrete system in Klein space? And in fact, that may or may not be related to tensor networks as in the ADS case. Let me just give the final end corrections. And obviously, there is some holographic duality that would be really tempting to explore. We would like to match these cold words to physical observables in the bulk and to their memory. Yeah. So thank you. Okay, that's all.
Thank you, Alfredo. Do you have some questions?
I was just wondering if you found a way to reconcile the fact that superrotations are generated by quadratic things in mu, but the stress tensor is mu d mu, and they don't seem to be related by a shadow transformation.
Good.
I think
So
following his question. Yeah.
You're referring to to this part, right?
Yeah.
Yeah, so the symplectic boson has mu d mu stress energy tensor. That is definitely a generator of super rotations in the sense that you have the right OPE for a stress energy tensor. Whether it's, I guess you're asking why that is not on the nose a shadow transformation of W2. That's.
I don't know if it isn't. I just integral
So
transform.
this W2,
becomes
I mean,
a contour integral or something localized.
I was very sloppy with the indices, but this is alpha dot, right? So this W2 is SL2R bar, essentially, while this part is the chiral part of the SL2R. Right? So this would be SL2R bar, and this would be SL2R. Yeah.
Okay. So there.
Sorry, does that answer your question?
Think so. Different helicities you're saying. One
Yeah.
is a negative helicity shadow stress tensor.
So this is like the loop. This would be the loop algebra of SL2R bar. Essentially.
Right. And I suppose you haven't tried shadow transforming that super rotation generator.
No.
To directly see if it. Okay. Fine.
Thank you very much. Right, I'm just getting slightly muddled about the discretization then. So the discretization looks to me like you're expanding in modes on the world sheet. But then you were talking about it as if you were discretizing in the lambda coordinates. Whereas there, it's in the it's kind of modes on the world sheet coordinates. Is there? Well, I'm not sure if you can clarify that distinction. I mean, the MHP, we can identify the world sheet with the lambda coordinates, but high MHP degrees maybe not. Sorry, yes.
Okay, there is no lambda to begin with. So the whole system takes the topology of the celestial torus, or its Fourier transform, which is also a torus, but it's more like a discrete torus. And I just called the field that lives in such a space mu, and then I take the modes of mu. And it's true that mu is discrete, and also, so that's because I'm in a circle. But also, when I truncate the modes of mu by the theory of Fourier transforms, I only need to look at mu at endpoints, right? So now I cut off my modes, and then it's enough of looking at mu at certain points, which are also endpoints. But there is no lambda. So if we were to write down the generators, there would be a lambda that's conjugate that happens to live in a. If it's conjugate to these mu's and these mu's are discrete, then this lambda is also discrete. But that comes sort of after the construction.
But the lambda is a that's related to the x plus coordinates on the torus.
Mu is related to the x plus coordinate. So mu is a function. So here is the mode expansion, but mu itself is a function of the x plus coordinate.
Well, mu is a function of x plus.
Yes.
But is the lambda? Sorry, mu is a function of x plus, but is lambda identified with? Is lambda plus identified with x plus?
No,
it's not. No. Okay. Yeah.
But obviously that's the intuition here, right? So that would be, yeah. I understand why you are asking this, but so far there is no lambda. So the lambda appears only as a Fourier transform of mu. So it's a bit confusing to write lambda here. The incidence relation is confusing. Yeah. It happens in momentum space, but then it's space time. So yeah. Yeah. Yeah.
Are there more questions? Comments?
The fact that you have a C minus 2, do you have a problem with unitarity? Or?
All right. So usually unitarity bounds C to be positive. I was under the impression we bypassed this in the 1,1 signature, but I actually may be wrong. I haven't done the exercise. All I can tell you is that these mu's are now living in 1,1 signature. So, I mean, maybe Lionel can answer this question from the nonlinear sigma model perspective.
I never asked them. It's almost there.
Almost certainly not unitary. Okay. There you go. Okay. Okay. I was under the impression maybe there was some loophole. Yeah. Maybe it's not certain. Yeah.
Also, you write the commutation ratio plus and mu minus, but you never write with mu plus, which are.
Oh yeah, those are no. Sorry, I write it. It's 0, right? So it's just it's 0 at least at the order where we are looking. Yeah. So it's an epsilon. Sorry. Yeah. Because we want to have SL2R symmetry. Sorry, we want to have a symplectic. Yeah. So this is like the SL2R tensor.
Okay. Thank you.
Okay, are there any comments, questions? If not, let's thank Alfredo again.
Is connected to in the new alpha you have an eye.
Yes. Yes. Oh, that's the one from that's one thing for this the anti for this I here. So they are only the creator, but they produce the it's the inverted is that eye connected to the CMI? Oh, yeah.
Bueno, gracias. Creo que